If you agree, we can now start the webinar. So welcome to all of you for participating in the second edition of the IG webinars for Southern Europe. We have 8 speakers from Croatia, Greece, Italy, Malta, Spain, Serbia, Slovenia, and Portugal. That means we have the best of the best. And we are going to start with Greece, Aliki Konsolaki. She's going to talk about innovative techniques for mapping surface and subsurface landforms with high accuracy using unmanned aerial vehicles and terrestrial laser systems.
Hello to everyone. Today I'm going to show you about the innovative techniques that we use for mapping surface and subsurface landforms with high accuracy using unmanned aerial and terrestrial laser systems. Okay, all right. So a few things about our equipment that we use. We use, as I said before, from the title, we use unmanned aerial systems. So we have a DJI Phantom RTK for scanning the areas with the UAS. And we have, on the other hand, terrestrial laser scanner. We have a Leica P50. And we also use handheld laser scanner, like a BLK2GO. It depends about from the environment that we have to scan, we have to study. It depends on how we will use it. We will use terrestrial laser scanner or handheld laser scanner. Furthermore, we have GNSS RTK system that we have for the measuring of ground control points or targets that we use in order to reference our models. And we have used as well total stations. We have a Leica FlexLine for measuring targets that the GNSS RTK is unable for us to use. So a few things about our methodology. We separate our methodology in 2 parts. The first part, as I told you before, concerns the UAS acquisition, data acquisition. So we have the flight procedure first, which is equipped with a GNSS antenna with a drone. From this flight procedure, we can extract the raw images, which we then align. We do the photo alignment in order to generate dense point cloud, a digital surface model, and an orthomosaic as well. For these procedures, we use August's Metashape software in order to have the final model. On the other hand, we have the LiDAR interpretation. So after the scanning procedure and establishing the TLS basis, we do the GNSS measurements. We have the scans, the TLS basis in order to scan the environment we want to scan. So with this procedure, of course, we have, as with the UAS as well, we have the point cloud generation, which we have to do to merge each point cloud in order to have the final model. And in order to merge the point cloud, we use cloud-to-cloud commands or target commands in order to have accurate results and a good combination of the point clouds. For this procedure, we use the Cyclone software. And after we have the Cyclone software and we have the terrestrial laser scanning results, we have the UAS as well on the other hand, and we combine all this together to have the final model. So now, with more detail, I can say to you that the use of UAS technique, we use RTK capabilities in order to have really accurate results. And it's really important in model in the exact position, the real position with the real coordinates, X, Y, and Z coordinates. That's why not even we don't use only the RTK capabilities, but we also use GCPs around the area that we are interested of in order to have better results. And also we can use the RTK GNSS antenna because sometimes the GNSS might not be so accurate. We might have not a good signal, so we use the RTK GNSS antenna in order to get even better results. We do several flights in order to cover the area that we are interested of, and we have to have high overlap percentage in order to for our results to be better, and with a great resolution, of course. In the second part of our methodology, we use the laser scanning system. So as you can see in the photos, we established the laser scanner to a base and in a tripod, and we scan the area that we are interested of. And then we have some targets here in the left image, which we measure with topographic methods in order to be able to combine the point clouds then together and have real coordinates. Of course, sometimes because the equipment is really heavy and difficult to use in some environments, we have also the BLK, which is a handheld laser scanner that we walk through the environment that we want to scan. And by using the BLK, we have extra results in some environments that it's hard for us to reach by the TLS. So now I'm gonna move to some case studies that we are used our methodology. So the first case study is in Myrtos Beach in Kefalonia Island in Greece, of course. So a few things about the study area. The area of Myrtos Beach is an 800-meter long beach. Is a very popular beach with many visitors every year, like millions of visitors every year, and it's at the northern part of Kefalonia Island. The beach has a relatively, I keep talking. Okay, the beach has a relatively small width, an average of 90 meters, and surrounded by rather steep slopes.
No, entonces si lo cierro, esto es lo que no me gusta del zoom. Si no vuelve,
cobbles and boulders. So rockfalls are being recorded very often there, especially after earthquakes, which is frequently a phenomenon of this section of the Hellenic Arc. So now, what happened and triggered us to study this beach? It was the Medikenianos that happened in September 2020 and affected the Greek territory and especially the Ionian complex and the island of Kefalonia. It was a rather extreme event. As you can see, the total rainfall reached like 230 millimeters, so it was really extreme for the Ionian complex. And of course, it affected the Myrtos Beach as well. So the first phase of our data acquisition was on July of 2020, like 3 months, 2 months before the event of Ianos happened. We went there and we surveyed with terrestrial laser scanners and unmanned aerial systems. So we had the data before the event happened, and erosion and deposition of the debris. So you can see that with the blue color is the erosion that occurred, and with the red one is the deposition of the debris. So we were able, by this technique, we were able to measure the erosion and deposition, and to measure the volume, the real volume of this. So we had like 1,300 cubic meters for the erosion, and 15 for the deposition. Now I'm gonna move forward to the second case study. We also did the study of the sea beach, which is again in Kefalonia Island. It's a really narrow beach with steep cliffs of clay, and this is the reason that it was really interesting, this case study, because of the narrow area of the beach. We had to establish the base of the TLS in a small island across the beach. So we had to swim through the in the interior of the sea in order to establish the TLS base in the small island that we found. And by this way, we were able to scan all the area and the clay cliff in order to have our results and the point clouds. Now you can see here the bases that we established. Here is the base 1, the base 2, and the base 3 was in the island that I told you across the beach. And of course, you can see here is the base 4. And you can see as well with this that we say KEF 14 and etc. is the GCPs, the targets that we used in order to combine all these bases together and have a combined point cloud. Here you can see the model, you can see the point cloud, the combined point cloud, so you can see the connection that each station had to each other. We did this connection, we did this composition, and we had a really accurate result. As you can see, the bundle error was like 5 millimeters with an overlap of 60%. And we managed to extract a really dense point cloud of 336 million points. So you can imagine the data, the big data that we had, how difficult it is for us to use, and we need a really good software and hardware in order to be able to process this big data and have a good result. So this, on the other hand, we have the unmanned aerial system technique that we used. So we had to use photogrammetric processing to have not only the cliffs, the clay cliffs, but the area above it. So we used the unmanned aerial systems, and here you can see with the yellow place that we had This is the area that we are managed to do with the terrestrial laser scanning system, and we have also the unmanned aerial system procedure. So we were able to combine all this together. So you can see now in this image the point cloud above, that it is extracted from the unmanned aerial systems, and the TLS with the more brown color, which is, you can see that it's separated. So we have on the cliff with really dense point cloud extracted from the TLS, and also we have the area above it with the unmanned aerial systems. So now you can see that this technique is very important because we can measure some events that we can find, some rock falls or landslides. So you can see here that we have the July of 2020 data set. This is a point cloud. It's not an image. It's the generated model. So you can see in the 2020 of the July of 2020 that it's a clear beach. There is no rockfall events. And on the other hand, you can see on the October that a rockfall event happened, and we can measure and we can volume this rockfall events. Now,
Aliki,
to
can
move
you
to
hear me? Aliki, you have 1 minute.
Okay, I'll be quick. To end with our third case study was Melisani Cave, which is a really interesting case study that we had because we were able to scan the entire cave, the interior and the exterior of the cave. So I'm gonna skip these slides because it says some information about Melisani Cave. So we were able to do the UAS scanning procedure from the above of the cave, and on the other hand, we were able to scan the inside, the interior of the cave with the TLS and with the handheld laser scanner as well. So we were able to combine this together and have the result, as you can see here. So it's really important because we have not only the 3D model, but we can also measure the width between the surface above the cave and the cave inside. So this is a unique procedure for these case studies. Of course, we did some geomorphological maps of the cave, and we were able to quantify the formations, the speleothems of the cave, the stalagmites, the stalactites, the columns, the gores, the lakes that we can find inside the cave. So we have a complete geomorphological map of it.
Sorry, Aliki, can you move
Yes,
to
I'm
please?
finishing, yes. So we had also, we did the rockfall risk areas, and to conclude, the use of this interdisciplinary approach concerning the use of close-range remote sensing equipment is innovative and adaptive to any landscape and environmental conditions, and provides detailed information about the topography and morphology of a landscape over time. It's really important because we need very high accurate results and very high accurate data in order to have a good integration of digital products. The 3D models can be used for the representation and further study in terms of geoheritage, geoconservation, monitoring natural hazards, quantifying landslides and rockfall events. And overall, the use of this technique can provide valuable insights into the processes that shape the Earth's surface and can be used to develop effective strategies for managing natural resources and mitigating the impacts of natural hazards and climate change. So thank you very much for your attention.
So today I will present the work that I did with a couple of colleagues, and also I have to say with an army of cavers who did the research in the system about which I'm going to talk. So the title is Morphogenesis of the Karst system of the Crnopac massif, which is located at Velebit mountain in Croatia, and it is a part of Dinaric karst. Okay, I have a problem with clicking. Okay, so Crnopac massif is highly karstified area in the southernmost part of the Velebit mountain. As I said, in Croatia, within the Dinaric karst. Here we can see the location in the square, and we have a closer look. So this is the massif, and the dots are cave entrances. So as we say that it is highly karstified, that is shown on this digital elevation model, and those dots represented caves because there are more than 300 cave entrances for now. And by each week and month, we are exploring more and more cave entrances in this karst massif. So what is specific about this cave system, karst system is that it hides cave system Crnopac, which is the longest cave in the Dinaric karst, and it is completely within the karst massive Crnopac. So here I put the topographic plan from the latest research, but also as the exploration on the surface of Crnopac massif. It is the same in the inside of the cave system, because every week and every month there are new explorations and new channels discovered. So currently it is actually more than 59 kilometers long, and it is 830 meters deep. Why I am talking about this cave system? Because it is the key point in our research, because we did the research on the cave system to explain the morphogenesis of the whole karst system. So now I will show some parts of the cave system. We can see at the bottom the lowest parts, which are epiphreatic and phreatic, which look like this. Then we have fossil zones with horizontal and vadose channels. This one is one big fossil channel, and we have vertical vadose channel, which are they can be like really deep and continuous, as you can see also on the map of the cave system Crnopac. So the aim of the work was to determine the basic forms, conditions, and processes of morphogenesis of Crnopac cave system, but also of the Crnopac massif and all the other physiographic units that I will talk about in this presentation. So methods, we use the digital elevation model geomorphometry, geomorphological mapping in the cave and on the surface. We did statistical analysis of speleological data and analysis of basic geological and climatic conditions in which everything is happening. So when we are talking about the karst system of Crnopac massif, we have to talk about three physiographic units. So we have at the northern part of this map is the first physiographic unit, which is called Gračac polje, with Ponor zone at the south rim. So Gračac polje is in the contact with Crnopac massif. I will try to activate the laser so I can show. So this is the southern rim of the Gračac polje and the contact with the Crnopac massif, where we have polar zone of karstic rivers. Gračac polje is at 550 meters above sea level. Then we have the central part, which is Crnopac massif itself. Its highest point is Veliki Crnopac here on this ridge, and it is 1,404 meters high, but mostly all the surface of the Crnopac massif is between 900 and 1,200 meters above sea level. Then in the south, we have karst plateau, which is at 200 to 400 meters above sea level, and it is slowly sloping towards the west to the Adriatic Sea, where it reaches the erosional base of the Adriatic Sea. So we have sinking water from Gračac polje, which is flowing underground through the Crnopac massif towards the south to the valleys of the Krupa and Zrmanja river. Those are these canyons carved into this plateau. And this plateau is actually a local erosional base of the karst system. Now I will show you, this is a view of the Gračac polje, and this is the base of the Crnopac massif from one side. Then we have the surface of Crnopac massif. It is highly karstified, and as you can see on this picture, you cannot take a photo of the surface because everything is really dissected. And then we have a karst plateau. So this is the photo taken from the karst plateau looking to Crnopac massif from the other side. We can see the difference from the more humid northern part of Crnopac massif, and we can see scarce vegetation and rocky surface on this southern part of Crnopac massif. And as I mentioned, karstic canyons of Zrmanja, Krupa and Krnjeza rivers are carved into, as we can see on the pictures. And this is partially water coming from the cave system Crnopac and the whole karst system. So geologically, we have the structure of Crnopac massif. Here we have surface geology, but beneath it is mostly consisted from Jurassic and Cretaceous carbonate rocks, which are then separated by paleo-relief boundary from overlying Paleogene carbonate breccias, which are called Jelar breccias, and they are characteristic for Dinaric karst of Croatia. Then we have Gračac polje, which has a bedrock consisted of clastic and carbonate rocks, which are mainly dolomite, and we have karst plateau, which is consisted of limestones of the Cretaceous period. So when we talk about surface geomorphology of the karst system, again we have to talk about three units. So Gračac polje, which is a hydrogeological barrier with ponor zone, and allogenic water input, which is coming to the Crnopac massif itself, and karst plateau with deep canyons. I want to emphasize some elements of the map, such as dry valleys on the karst plateau, blind valleys on the contact of Gračac polje and Crnopac massif, and we have uvalas, karstic uvalas, and this presumed corridors of former surface runoff, and we have some denuded caves on the surface of Crnopac massif. So we have some traces in the relief, as example, as I said, series of uvalas and karstified valleys, which indicated the possibility of surface runoff of water from the Gračac polje zone into the south in early phase of the formation of Crnopac. Okay, to continue. I have to activate the video. So this is the surface of Crnopac massif. Itself, it is the most karstified part of the researched area. It is specific with numerous dolines with narrow rock ridges and karst towers between them that have formed. The doline density reaches value of 100 dolines per square kilometer, and they often reach a diameter of 80 meters and more, and their depth can be several tens of meters. They often have steep rocky sides, so also the research of this karst massif is not that easy, because it takes a lot to walk through these ridges and deep dolines. So to skip to the results of our analysis, this is a graph of a vertical distribution of cave channels in the area of the Crnopac massif. So main characteristic of the Crnopac caves is their morphological complexity. As if you can remember the slide where I showed the cave system map, you can see that it is complex. So it is consisted of leveled horizontal channels intersected by vertical or steep Wazaz channels. We can see on this graph that we have channels grouped in several height classes. The most pronounced is that at the height of 500 to 650 meters, which is 0 to 100 meters above the level of current Ponar zone, and includes the lower level of cave system Crnopac, the main part of some other big caves also on the Crnopac massif. So the next one we can see here, the next group of the channels is about 730 to 830 meters, which is 180 to 280 meters above the level of the current recent Ponar zone, which includes the upper parts of cave system Crnopac. Okay, here we have profiles, geological profiles of cave passages of cave system Crnopac and other bigger significant caves in the Crnopac massif. And we can say that the most important factor in morphogenesis is allogenic water input in the Ponar zone, and this is the thing which was constant through all the genesis of the karst system. The development of the karst system is related to the relative tectonic uplift also. So Crnopac massif is tectonically growing, so going up, and this led to lowering of the level of allogenic water input from Gračac polje, and consequently we have lower active conduits. We can see that every 100 to 200 meters we have tectonic stagnation, which is seen in leveled channels in cave system Crnopac. Also, we can conclude that the amount of water definitely was not the same through all the phases. We can also see that in morphology of the cave passages at different levels. And lithology also played a role in one part of Crnopac massif, and we can say that that happened in this highest level of cave system Crnopac, because we have a paleorelief contact of Jurassic carbonates and overlying carbonate breccias from Paleogene. And we also have those vertical passages which are made by autogenous seepage of meteoric water from the surface to the cave system Crnopac. And of course, it led to the formation of these big vertical channels which are intersecting with these grouped horizontal channels. Also from the geomorphological map, we can see that we have surface karstification, which is ongoing. So we have destruction of older parts of the cave system Crnopac. There is a lot to do more because we found some denuded caves as it was indicated on the geomorphological map, but for sure there are some more to find. Okay, so I hope that I did not exceed my time and this is it from me. So if we have time for questions or whatever, I'm open.
Hello, everybody. I'm really honored to participate at this webinar, and I think that International Geomorphological Week is really a great idea. I will talk about uvalas, a particular form of karst surface relief, and they are often contradictory or excluded from classifications, so it's really a kind of pro et contra presentation. This presentation I dedicate to my late professor, academician Andrej Kranjc, who was my PhD supervisor at the University of Nova Gorica at the karstology program. And at the very beginning of my studies, in one of our discussions, he asks me, do you know exactly what are the uvalas? Not many papers on this. What are they? And he thought that we should keep this term in our karstological terminology because it's a typical Dinaric term, and that we should keep it. So in agreement with Professor Kranjc, I took it as a subject of my dissertation at the University of Nova Gorica. Here are some notes about the toponymy. So where we have the term uvala present, regardless of the science and morphology, it's in toponymy at some places within the study area. So we can find them generally in Croatia, Bosnia and Herzegovina, and a few in Western Serbia. Mainly in continental Croatia, in Lika, in Western Bosnia and Western Serbia. So they are used, these names are used for large karstic depressions. But along the Croatian coast, this term denotes a small gulf on a seashore. So we have a kind of terminological problem because it has a dual meaning. But anyway, even along the coast, the uvala is a form which associates with a depression. It's not the same origin, but it's a lowered area of relief. In the Croatian inland, there are several terms which are used. So besides uvala, there is a draga, duliba, which is characteristic for northern Velebit karst, or korito in southern Velebit. While in Slovenia, it is not used in ordinary language or toponymy, but there we have draga, dol, or alpine depressions called kontas. And in Montenegro, the terms which dominate are do and ugli. So we all know that there are terms from the Dinaric karst in international terminology, and we are trying to push them also wider. So uvala is, as opposed to dolines and poljes, uvala is somehow overwhelmed with many questions, and it is not so clear internationally. Professor and my colleague Andrei Mihevc, you know him for sure, he used to say that Jelena, uvala, the morphology of uvala is like a morphology of a potato. So there is, it is something extended, but it can have so many forms. It was a bit of joking. And the introduction of uvalas to scientific geomorphology came by Jovan Cvic, who, after his PhD studies in Vienna, he first mentions uvalas in this paper related to the mountains of Bosnia, Herzegovina, and Montenegro, but the term is just used, not defined. However, in the karst poljes of Western Bosnia and Herzegovina, there is a detailed analysis, but applied through the cyclic concept. So what about this cyclic interpretation? How come? In 1899, Cvic was in the field with Albrecht Penck and William Morris Davis in the Dinaric karst. And Davis was one of the leading geomorphologists of that time. And the idea of cyclic evolution of fluvial relief was one of his main contributions. So for Cvic, he was still young at that time, relatively, and the application of that model on karsts, it was his scientific challenge. So he tried to make a concept of that the dolens evolved to uvalas and uvalas evolved to poljes. But however, at the end of his career, and this La géographie des terrains calcaires, it was published after his death, but it says that he actually abandoned that concept, but because it's hardly applicable to karst, because the erosion does not act as normal erosion out of karst. But in the second half of the 20th century, there were a number of unclear and inconsistent definitions. Many definitions considered only the dimensions, so it's something in between. There were either negative definitions. Well, it is something which is not a doline nor a polje. Then a cyclic model, which is like they are formed by coalescence of dolens, with but it was opposing both the model and the term. So I think uvalas were a victim of that cyclic model, which turned in the end wrong, but many people just remember that as wrong, and then uvalas were wrong generally. And on the other hand, there were also opposite extremes, especially in Serbian literature, which I was opposing all the time afterwards. There were two wide definitions. So they thought that blind valleys, widened parts of dry valleys, so anything which is like a lower relief within karst, that were uvalas, which is of course not correct. And key karstological references from this period, end of the 20th and beginning of the 21st century, they either don't mention the term uvala, or it is mentioned in in negative or outdated contexts. And some of the comments for abandoning is, for example, in Lowe and Waltham, they said, like, for features of intermediate size, I use compound sink, William White. And Lowe and Waltham, it's no longer accepted, and the term uvala has fallen into disuse. And maybe the best comment was by Arthur Palmer, who said that this term needs to be either more clearly defined or abandoned entirely. And so it was one of the triggers for me and Professor Krantz to try to keep it and to take a more closer look and to systematize. So that was a motive for the new research. I took 43 examples from the Dinaric karst and the Carpato-Balkan karst in eastern Serbia. There were detailed geomorphologic analysis with the construction of detailed 3D models. Then I applied structural geological mapping for 12 of them, following the method of Jože Čar, the geologist from Slovenia, and also the applications for terrain analysis. And the study area was in the Dinaric and Carpato-Balkan karst, and you can see mainly, and these locations are mainly the locations where the uvalas are the best. So the results speak in favor of abandoning the cyclic concept because it is not good, it is not applicable here. But at the same time, I tried with this study to support the status of uvala as a particular form of karst surface relief, like irregular forms, which shouldn't be doubted anymore. So this is one of the rare real uvalas in eastern Serbia. There are not so many. And I tried to suggest a new definition. So they are always in kilometer scale. All of those which are discussed were at least 1 kilometer in diameter, mostly elongated or totally irregular. Bottoms with dolines, which does not mean that they are formed by coalescence of dolines, but on the contrary, dolines are the secondary form. So sometimes they are flattened with colluvial sediments and always above the karst water table. So there are no confusion with poljes. So origin and development, according to this field study and field mapping, it is very clear that it is strongly guided by tectonics. So as I took this definition by Professor Šušteršić that genuine nature of karstic processes is not lateral planation but dissection. So it is not good to say that uvalas can further form poljes. Uvalas are high in the vadose zone. And the identification with other landforms should be strictly avoided. So these results were taken into account at some following publications. So the second edition of Encyclopedia of Caves includes the explanation and why the term was neglected and the reason, discussion on former karst cyclic concept. So after the revision, it was used in several capital publications. And for example, in this part, Professor Ugo Sauro mentioned in his chapter many things also about uvalas. And also in the brand new book by Jode Vele and our host, Professor Gutierrez, the results were also taken into account. So that's why I hope that uvala will survive. And further on, I found also some citations, even by colleagues in South America, etc. So I hope it will survive. And for the end, and for your thank you for your attention, I will include the champion among the studied uvalas. So it's a Klekovačka uvala in Bosnia, which the depth of which from the highest closed contour is more than 200 meters. And you see that how large it is. So it deserves the place among the most stunning phenomena of Dinaric karst. Unfortunately, it's all covered in woods, so it's not really easy to show the actual forms. So that would be all. And if we have some time, I can answer some questions.
Good afternoon, everyone, and thank you for the opportunity to talk today. My name is Jorge Sevil, and I'm a PhD student from the University of Zaragoza in Spain. I study sinkholes from the geological hazard perspective, and today I would like to show you how something rather simple at first sight, such as multitemporal mapping, has important implications for spatial predictions and can serve as basis for hazard assessment. I will illustrate this with data from a study area on the western shore of the Dead Sea. First of all, where's the Dead Sea and what's going on there? As you already probably know, in addition to being the lowest land-based elevation on Earth, the Dead Sea is a hypersaline endorheic lake located in one of the pull-apart basins developed in the transfer fault system between the Arabian Plate and the Sinai subplate. Currently, this basin is divided in two and separated by the Lysan diapir. The southern one used to be flooded by the Dead Sea, but nowadays it's occupied by industrial evaporation ponds. And you can see on the right image, in 1972, both basins were connected. What happened? Well, the Dead Sea lake level has been declining for over a century. What you see here is the evolution from 1972 to 2011. This trend continues at present time. The decline is mainly caused by the increment of use of water in the catchment, mainly by the diversion from the Jordan River along an arid region increasingly populated. and it's pumping of water to evaporation ponds of the southern sector for potash production. The anthropogenic retreat of the shoreline and the accompanying base level drop have induced and enhanced several hazardous geomorphic processes, such as fluvial downcutting, mass wasting processes, and subsidence. The most striking effect has been the generation of thousands of sinkholes that, despite the damage, provide an exceptional opportunity to study sinkhole hazard evolution. Since the 80s, the decline in the Dead Sea lake level has been accompanied by the formation of more than 6,000 sinkholes that have completely changed the landscape and resulted in substantial damage on human structures such as roads, touristic resorts. This is a camping area near Engedi, and this is a large sinkhole affecting Mineral Beach, touristic resort that need to be abandoned. The next question I would like to answer is why sinkholes form in the Dead Sea. Sorry. Oh. Okay, now I will do it with assistance of the area I've been studying these years, which is located on the western shore of the lake, south of the Nahal, Hassanon alluvial fan, and the touristic resort I just showed you. The study area is bounded to the west by the western boundary fault that in this sector juxtaposes the Holocene Selim laminated sediments, the downthrow block, against the late Pleistocene Samra and Lysan formations, which are underlain by the Cretaceous Carbonic unit of the Judean Mountains. From west to east, the study area displays three morpho-sedimentary environments underlain by interdigitated deposits, a strip of colluvial deposits from the erosion of the fault escarpment, alluvial fans that consist of the slightly cemented gravels, and mudflats exposed by the anthropogenic decline of the lake level and underlain by the Selim formation. According to borehole data, this formation reaches up to 70 meters in thickness and comprises interdigitated alluvial and lacustrine sediments. Its lower section is made up of a porous and poorly lithified salt unit up to 25 meters thick and mainly composed of halite crystals. There are three main models, compatible all of them, that explain the dissolution of the salt unit by undersaturated water that reaches the salt from the bedrock aquifers flowing outwards along concealed faults that reach the halite. This is the halite unit. Shallow groundwater from the marginal alluvial fans gravels that dissolve the salt unit along its edge, and percolated via sinkholes acting as shallow holes during flash floods. Now that we have an idea why this is happening, how can we study sinkholes and their evolution? Well, for this presentation, how about with multitemporal maps? This mapping approach is rather self-explanatory. In this case, we produce sinkhole maps with intervals between 1 and 3 years using various types of imagery, aerial photographs, satellite images, and ortho images. The latter were produced for this work by structure for motion photogrammetry with images taken by drones in 2018 and 2021. With all this data, I carry out the multitemporal mapping manually with assistance of GIS software on various types of imagery. And between 2005 and 2021, I mapped 900 different sinkholes and more than 2,000, including their evolution in time. Then I calculated a number of morphometric and spatial parameters by a combination of GIS software and R packages to obtain a vast amount of data about the sinkholes and their evolution. The main result looked like this. There's a lot of data here, and I will come back to this figure, but what are the implications for spatial prediction? How can the collected data serve as basis for sinkhole hazard assessment? Well, it's essentially based on two elements: data about the morphometric and morphological evolution of the sinkholes, and information about the spatiotemporal parameters that they have following times. And then once we have a better understanding of how they behave, we can apply a kind of reverse uniformitarianism with the working hypothesis that future sinkholes will behave in a similar way as they have done in the past. This is a very powerful approach, but it has one particular limitation that I will discuss at the end, and that has been addressed in other geohazards. So this was the main result. This is the evolution of the study area between 2005 and 2021. It shows the formation of new sinkholes, their growth, coalescence, as well as the lowering of the Dead Sea Lake level. The sinkholes map are distributed along an elongated and narrow strip where they tend to form tightly packed alignments and clusters. These lineaments are roughly parallel to the Dead Sea Western Boundary Fault system and have similar trends to the faults detected by means of geophysical methods in previous works. It's like mapping faults. This slide shows the evolution of different sectors of the study area between 2018 and 2021. It evolved through various processes. New sinkholes form isolated or nested within previous ones. I would call this in red redundant sinkholes. Another simple group by mass wasting processes, such as further collapsing of the roof, toppling, and slumping. This process plays an important role in the aerial expansion of sinkholes located in the mudflat after degeneration. Doing fieldwork, we also learned that in some cases, the collapses are preceded by gentle sagging. This is the way it looked in the field. And this is what we found 3 years later. 3 large sinkholes appear in between 2 compound depressions, and nowadays all of them are part of the same coalesced structure. As you can see, the evolution can be quite fast. Because of the strongly clustered distribution of the sinkhole, coalescence plays a huge role in their evolution. It can occur both by the generation of new sinkholes in between or by the expansion of pre-existing ones. Here you can see some of the maps showing the evolution of sinkhole density expressed as a number of sinkholes by a square hectometer. For example, the highest density occurred in the southern zone in 2011, and then it decreased in time due to sinkhole coalescence. But in the central sector, the youngest one, sinkhole density showed a general increase over the whole investigation period. The landscape shows differences regarding the maturity of the sinkhole clusters. For example, this cluster located on the southern sector display an elongated and tightly populated sinkhole lineament formed both by individual sinkholes and compound ones, with the highest density values measured in the study area. This area most probably will evolve to something similar to what we can see today at the north, where sinkholes evolve into a couple of very large compound depressions, representing hundreds of nested and coalesced sinkholes that display a hummocky topography, which is where it is quite difficult to distinguish between sinkholes. In addition, by fieldwork and detailed mapping, we found that 80% of the sinkholes mapped in 2021 were located inside the perimeters delineated by sets of concentric fissures. The evolution of their maximum extent from 2018 in purple to 2021 in red shows a stabilization of the western margin and a general growth towards the east. This means that not only there are cavities being formed within the salt that could generate sinkholes at the surface, but also there is a dissolution front advancing towards the receding Dead Sea shoreline, which is accommodated by flexure and crack generation at the surface. Before concluding my presentation, I would like to show you that with all the information we gather about the spatiotemporal evolution of sinkholes in the study area, characterized by a high degree of clustering, we were able to produce susceptibility model only based on past sinkhole occurrence with a high prediction capability. For example, creating a high susceptibility zone using buffers 50 meters to the west and 100 meters to the east from an axis connected antipodal points of the main sinkhole cluster from 2008. This is something like this, sorry, yeah. We were able to predict 83% of the new sinkholes forming in the decade after. There is between 2008 and 2018, with only 19% of the study area classified as high susceptibility. This is a very good prediction capability. We also learned about the peculiarities of hazard assessments in highly dense sinkhole areas. For example, as new sinkholes form in a restricted area, the available space gets reduced, and therefore many new sinkholes start to form nested within pre-existing ones, fully nested or sometimes partially. This feature strongly affects sinkhole hazard. Typically, it could increase with the generation of new sinkholes, but because of the redundancy, not all the new ones expand the area affected by subsidence. Therefore, when conducting hazard assessments, we should not consider all the new sinkholes formed, but the effective ones, that is, the new non-redundant sinkholes. But, and I will finish with this, what about the trend of generation of sinkholes? Is it going to remain constant? Usually, we cannot study this because of the typical slowness of the process of dissolution and sinkhole generation. Yet, the rapid development in the Dead Sea offers an exceptional opportunity to study their evolution. Here you can see the number of sinkholes from each year interval for 16 years, and the annual spatiotemporal frequency. Besides the increment in redundancy that I've been talking about, this plot shows a decrease of the sinkhole hazard by frequency in time that may be temporary, long-lasting, or even boosted, and it could be related to a number of hypothetical and highly verifiable reasons beyond the reach of this presentation. This means that sinkhole hazard is a non-stationary process that can vary in time, something that has important consequences on future predictions and restrict the extent to which we can continue to apply this kind of reverse uniformitarianism when conducting hazard assessments. Thank you very much. It's been a pleasure. And if you have any question, I will be glad to answer them.
Great. Well, thank you very much to the organizers of the EIG Southern Europe webinar. I'm here today to represent the Portuguese Association of Geomorphologists, and I'm going to be talking as Ephemius mentioned about storm-induced morphodynamic processes and their geomorphological impacts in coastal barriers. My presentation is going to roam around different locations around the world because I've been working across different institutions for the last few years, and this work reflects a little bit that. So for many of you that work in coastal geomorphology will know that storm impacts in coastal barriers or in coastal systems are commonly conceptualized according to the magnitude of the forcing and the characteristics of the morphological setting. So, in one side we have the waves, the tides, and the storm surges. On the other side, we have the characteristics that are geomorphological characteristics, and they can be considered in isolation, but the reality is that we need them together. So while we can have high flooding hazards when you have high storm surges or we have high tide levels, and then that can be combined with high waves to lead to high flooding and high erosion hazards. The reality is that the receptor that we have also influences the response that it's observed. So in erosion hazards and flooding hazards are relatively low in hard rock cliffs, and they will be increasingly, they will increase as systems become more susceptible to the hydrodynamics. So in a way, we have more extreme responses in systems that are composed by low and narrow barriers, systems that have relatively little morphological kind of elevation. So the integration of these two components is fundamental so we can understand what happens on the coast. And because of the integration of these two components is so important, this relationship between the forcing and the morphology to distinguish the impacts of storms was very elegantly integrated by Salinger in 2000 in the storm impact scale. Okay, in the storm impact scale, and fundamentally this storm impact scale looked at the morphological characteristics determined by the height of a dune, the height of a barrier, and also the base of the dune or the base of the barrier as our core morphological characteristics. But then on the hydrodynamics, we have the contributions from the storm surges and from the tides and from wave setup that determine our minimum or maximum still water level. And then on top of that, we have waves that combined with tide, storm surges, and run-up allow the onward movement, the swash motions, to reach parts of the coastal system. Salinger proposed fundamentally four impact regimes, and these nice animations give us an idea of what the different regimes look like. So if we start with swash, we fundamentally have conditions that in small storms, conditions that the waves reach the beach and they erode the beach, but they don't really reach the dune. So in this type of condition, we have relatively limited morphological change. I don't know where it stopped. Then as wave height increases or water levels increase, then we start to have waves that can progress all the way until the base of the dune, and they start to collide with the dune. And so we enter a collision regime where dune erosion starts to happen. As the water levels increase and the waves also become more energetic, we're starting to get water going over the top of the dunes or top of the barriers, and creating what's called overwash. That starts to contribute to erosion of the dunes and also increased flooding of the landward areas. And then when things really get really bad and storms become extreme in terms of the combination, particularly in terms of the combination of storm surge and tide levels, and we have full-scale inundation. So these four impact regimes are very useful, and they're very extensively used nowadays to analyze coastal hazards, to kind of try to characterize the potential for erosion and the potential for flooding, for integrating into early warning systems. However, the storm impact scale has a series of assumptions, and the type of application assumes that storm responses are overwhelmingly two-dimensional, and they are determined fundamentally by cross-shore processes. So we're thinking about a system that operates in a kind of a profile way. And here we're also only considering the storm water level determined by the wave height, by the tides and the storm surges, and the swash motions determined by the waves. So we leave aside a wide range of other mechanisms that happen on coastal areas. So these assumptions of the storm impact scale hold for many exposed coastal barriers, but there are a range of three-dimensional morphodynamic processes that also play a key role in determining the geomorphological impacts to coastal storms. So this is going to be the core of my talk, because I'm going to be fundamentally talking about three different morphodynamic processes and how their impacts in terms of coastal erosion, and how they are necessary, or how we need to consider these as well when we're looking at a local scale erosion and flooding. The first of the processes is going to be that I'm going to talk is storm-induced rip currents and cellular circulation, and I'll use 2 case studies from Portugal. And then I'm going to talk a little bit about storm-induced beach and nearshore rotation, using an example from Portugal and an example from South Africa. And then finally, I'm going to be talking a little bit about the variability in overwash potential in barrier systems, using examples again from the south of Portugal, but now also from North Carolina. So in terms of storm-induced rip currents and cellular circulation, it's important to note that rip currents are not traditionally associated with storm morphodynamics, but they can develop in embayed beaches during energetic waves or during storms. So rip currents usually developed because there's an along-shore variation in wave height along the beach, and that leads to the development of cellular circulation. However, when there's a storm, usually the storm waves become so energetic and the surface zone becomes so wide that circulatory mechanisms like rip currents tend to be erased or disappear. However, in embayed beaches, because we have headlands, so in this diagram you can see the headlands or the boundaries represented by this dark brown. When we have headlands and boundaries, these constrain the surface zone circulation, and they kind of lead or reinforce the potential for rip currents to develop. So in bait beaches or in bait settings, we have the development, usually the development of storm-induced rip currents. And depending on the site-specific characteristics and the orientation of the wave approach, we can have a rip current, a strong rip current develop on the center of the beach. We can have rip currents on the extremes of the beach, or we can have rip current only on one side of the beach. So these storm-induced rip currents, also named mega rips, they generate very strong and very persistent offshore flows, and these contribute to extreme erosion. Yeah. So here, so the examples that I wanted to talk is Rifana and Amoreira beaches, which are located in the west coast of Portugal. And you can see the locations, and you can see here a little bit of an aerial view of the two sides, two clearly in-bait beaches. The black lines represent where we surveyed them for over 2 years. And here you can see the results of the surveying. So at the top, we have the wave height during those 2 years. And then here we have a line that represents the morphological change in terms of the volume of the beach in each of the 3 profiles for each of the 2 sites. And then we have some qualitative indications in the dots about the presence or absence of rip currents. The important thing to highlight is that over the period, over these 2 years, there was a very substantial sequence of storms. So over a period of a month, there were 5 consecutive storms with waves in excess of 5 meters, but also even reaching 7 meters. So quite an energetic event. And during that event, across the entire west coast or southwest coast of Portugal, we've seen extreme erosion. In the first site, we see erosion primarily in the northern and central profiles, while the southern profile doesn't really change that much. So when we're expecting an entire beach to erode and it doesn't erode and only parts of it erode, that means that there's some along-shore variability here. And then we looked into more detail, and we could find that fundamentally a rip current, a mega rip, developed in the center of the embayment, and that mega rip was fed by a feeder channel from the north. And that connection of a feeder channel in the north and a mega rip in the center led to extreme or enhanced erosion. In Arifana, the situation is similar, but not exactly the same. So we have a slightly more indented embayment with a very asymmetric type, with very asymmetric headlands. But what we observed here was that the center of the embayment didn't actually change, quite almost nothing, but the extremes of the embayment changed quite remarkably. Here again, on further analysis, we have identified the presence of mega rips in these two, in the extremes of the beach, and these led to a very extreme erosion. Just to give you an idea of what a mega rip looks like, here is a couple of panoramic photographs of Rifana Beach during the storm. And what we can see here, and you have to kind of use a little bit your imagination, but fundamentally what we see here, and it's highlighted by the black line and arrow, is that we have a flow coming into this direction, and that flow is actually visible because it's changing the wave breaking, and it flows, curves, and moves into the center of the embayment. So this is the northern mega rip. And in the south, it's less visible because we're further away, but we can see the plume on the end and the jet channel of the rip head. Things are much clearer after the storm has passed because the morphological signature of the rip currents has been left on the beach. And we can see very clearly the presence of 2 channels that come, the feeder channels that come from more or less the center of the beach. And then the exit where the main rip channel was located in each side. So these are highly alongshore, non-uniform mechanisms, but they drive extreme erosion of in-bait beaches in many locations exposed to energetic forcing. Now we move into beach rotation, and beach rotation is a significantly different mechanism. And for those that are non-coastal geomorphologists, rotation fundamentally corresponds to the alternating morphological responses between opposite sections of an in-bed beach. So basically, under wave forcing, one side of the beach erodes, while the other side of the beach accretes. Beach rotation can happen at a range of timescales, from very long decadal timescales, but the focus of my talk is on the short term. And on the short term, beach rotation tends to be driven by gradients of longshore transport, and these are created by either by bidirectional wave climates or by a longshore variability in wave height. Going quickly through the two case studies, because I'm keeping an eye on the watch. In the first case, rotation was observed during a monitoring for 2 years in the south coast of Portugal. And here we have just an analysis of the data using principal component analysis, or BOFs. And what we've seen in the data set is that the main mode of change in this beach in response to storms is a cross-shore uniform response. So the entire beach erodes and then it accretes in the post-storm once it's under post-storm conditions. And that's negatively correlated with the normalized wave power. So it makes sense. Big waves lead to lower sediment, and small waves contribute to increased sediment. So that's the relationship here. And it happens primarily, or the best correlation was found at intervals of 10 days. So it's slightly longer than a week for the response to be most evident. But we also seen a rotational response in this case, because we observed that in some parts of the beach would be, or in some periods, the beach would be accreting on one side and eroding on the other one. And so we have this alongshore opposing pattern that justifies about 30% of the morphological changes. This is then correlated with braking direction and with longshore energy flux. And we can see by the time of the correlation, which is slightly shorter, that the rotational response to storms is more effective or more efficient or rapid than the cross-shore response for this case. Another case that we've explored was in the south coast, in the east coast of South Africa. And here what we've seen is that because we were lucky enough to be able to do a series of bathymetric surveys over winter, we could see that the rotation that was observed on the beach was also matched by a rotation on the near shore. So fundamentally, when we have the shoreline receding, we would see an erosion of the near shore. When we have the shoreline accreting, we have accumulation on the near shore. Just to put this into context, this is a little bit the opposite what we'd expect, because when we have erosion on the beach, we would expect accumulation of a sandbar on the near shore and not erosion. But that's what we're seeing in Isipingo in South Africa. This is a work that is still in progress because this confusing mechanism isn't very clear what might be driving, what's coupling the wave, the beach and the near shore. And we're using a couple of modeling tools to try to understand the role of wave energy fluxes and near shore circulation. And then the final mechanism that I wanted to talk was a longshore variable overwash potential. And overwash, again, for the non-coastal geomorphologists, is the wave-driven transport of water and sediment over the crest of a barrier or a crest of the dune. And it's fundamentally influenced by a range of geomorphological and oceanographic factors, particularly foreshore and nearshore geomorphology, but also grain size, apart from the waves and the storm surges, which are the oceanographic ones. To study overwash, we've been working in Barreta Island in the south of Portugal for many years. And over the course of a 2-year monitoring program, we've observed a range of variable overwash intrusion. Although the height of the barrier is almost the same across the entire system or across the entire barrier, the reality is the intrusion of overwash was quite different. And further analysis allowed us to identify that it had to do with barrier width and slope, also with nearshore morphology, fundamentally the presence of sandbars, but also with breaking wave height and breaking position. And we can see here a little bit the variation in breaking waves. And here we can see the variation in overwash intrusion over that period. To try to understand a little bit better what was causing it, this variation, we did a series of campaigns for more detailed analysis of overwash, and then model the overwash potential and the number of overwash events. And fundamentally, we were able to confirm that first, as you'd expect, wave height is the most important. Then nearshore bathymetry comes next, but grain size also influences overwash occurrence because coarser sediments allow more infiltration, so they reduce overwash, but finer sediments have lower infiltration, so they'll allow more overwash. So all of these allowed us to understand a little bit better what's the alongshore variable overwash potential in Barreta. And then we continue that analysis in Masonboro Island in north coast of North Carolina. And here we come to the same conclusions. So in the interest of time, I'm not really gonna explore this in much detail. There are slight differences. The nearshore morphology changes because of the presence of sandstone, not because of the presence of bars. But fundamentally, we're getting the same thing, that things change alongshore a lot more than applying a 2D cross-shore approach would allow us to understand. So to conclude, the main idea of my talk was to highlight that storm-induced erosion and flooding of coastal barriers often displays significant alongshore variability. And this is due to a range of 3D morphodynamic processes. And then makes us think a little bit if can we rely on 2D approaches for accurately characterizing erosion and flooding hazards, and then evaluating coastal risks for extreme storm events at local scales. Perhaps not. Perhaps at local scales, we really need to look things in 3D. And then with such wide variation, can we actually consistently determine storm-induced impacts along coastal barriers at regional to global scales? Because nowadays we want to be able to think explore things at global scale. I think that there are limitations. Clearly, there are limitations of 2D approaches, such as the one that the storm impact scale presents. But these still provide very good first-order overview of potential impacts of storms in coastal barriers. So this is something that my current work is exploring, and hopefully I'll be able to share with you in another opportunity. And then finally, thank you very much for listening. And I just want to mention that we've just opened for submission a special issue on geomorphology to look at recent research in coastal geomorphology. So if you're working on coastal geomorphology and you have a paper ready to go until the end of September, consider submitting to our special issue. Thank you very much.
Yes, so my name is Hiba Wazaz, and I'm presenting the subject of my master's thesis in coastal geomorphology. So I've been monitoring for seasonal sediment dynamics to Maltese pocket beaches. The aim of the study, again, just a master's thesis, so cannot be compared to years of study, although it makes me very eager to have more insights that you can get with years, was to study using 3 different methods, so the beach gradient, the granulometry, and the bathymetry. And also it was to assess this unmanned surface vessel, or USV, and that's the reason of my question, to see how this kind of small available tool can do bathymetric survey. So as for the site, so Maltese Islands are located in the central Mediterranean, just south of Sicily and the Malta Plateau. And they are composed of limestone of 4 different layers. The upper coralline limestone, which is harder, the blue clay, which is a clay, so it's very unstable, the globigerina, which is much softer and erodes very easily, and finally the lower coralline limestone. can also see all the different faults that we have on the island on the map on the right. As for the study sites, so it was 2 different small pocket beaches. So if you get to see the size of the beaches, they're about 200 meters length. And they are located on the north western part of Malta, which is mostly composed of cliffs and screes. And occasionally these small pocket beaches, either at the valley bed or at the bottom of clay slopes. So again, a nice picture to express this geomorphology, where you can clearly see the upper coralline limestone plateau laying on top of the clay slopes, which make it break down into screes. A very famous scree here in the middle that is called Arraba. And on the left, you can see Golden Bay at the bottom of the 2 hotels, unfortunately very urbanized beach area. And the second beach that was my study is the one at the middle, just left of the scree, which is much more natural and is at the bottom of a clay slope. As for Maltese climate, so obviously the Mediterranean climate with dry summers and rainfalls happening mostly between October and March. Most often the rainfalls are heavy and short, so they do influence easily beach morphology. And as for the wind climate, winds are mostly from the northwest, and most of the days are windy. It's even in summer quite hard to have unwindy days. As for the methodology I used, so first of all, I built these 3 transects, that represent a different part of Golden Bay, where the northern transect T1 represents the more urbanized part of the beach. The transect T2 is at the bottom of the valley bed, and the transect T3 it's at the more natural area. These transects were used both for beach profiling and for granulometry stations. So 15 stations were chosen on these transects, and these stations were further separated into station groups according to their beach zone. As for beach profile, I used a pantometer, which is a wooden frame with a protractor and a level, basically. And from it, I derived a beach profile starting at the back shore and from a fixed point of reference. As for granulometry, I collected about 7,200 grams of sands with a small corer on 44 stations overall, up to about 30 meters in the near shore, and at 2 different depths on the dry stations. Unfortunately, these depths didn't show any difference. So, I mean, at least we know that there's no difference in between 5 and 10 centimeters. The granulometric analysis further used sieves with mesh size between 75 micrometers and 16 millimeters. And the results were analyzed using the Gradistat software. As for the bathymetry, and that's again one typical topic as for near shore shallow bathymetry, which is hard to achieve with vessels usually. So I used this water drone unmanned surface vessel. Power Dolphin is its commercial name. So it's a completely available, ready to use commercial small vessel. It's about 60 centimeters long. It was originally marketed as a fishing aid to detect fish, but it has this power seeker, which is the small ball you see at the bottom. that is a sonar, a single beam sonar, which has depth detection between 60, 70 centimeters and 80 meters. And it has an accuracy of about 10 centimeters. From this point data, a quality control was led, and then an interpolation, of the points were done with an inverse distant weighting algorithm. So a bit more about this power dolphin. So now you can see the size a bit better. It has also a camera at the top that can film both under and above water, and two small rotors at the back, while the antennas give a range of connectivity with a remote control of about 100 meters, which is one of its downsides because it's quite short. It has several speeds, cruising speeds. So here you can see its faster speed that I use to cover larger areas during the surveys. And it can be associated with a smartphone to help both the navigation and to collect the bathymetric data. And here you can see the screenshot of the smartphone during bathymetric data, where you see the path of the USV and the preview of the depth. As for the timeline of this study, it was done between January 2020 and April 2021. So the beach profiling was done 16 times every month. The granulometry was done only 12 months up till December 2020. And the bathymetry was done 9 times. So now to the results. Here you can see all the successive beach profiles. So the blue colors correspond to winter, pink, violet to spring, red to summer, and green to autumn. You can see that between all months, even summer month, an observable change was happening. And we can also observe that the crest was formed during the summer month, and then during autumn, corresponding to the first large rainstorms, the crest was disappearing and the overall beach face slope was decreasing. So we observed the same on the 3 transects. Transects 1 and 3 were the most dynamic because of this beach rotation Carlos has been speaking about. So we observed the same thing here, and we observed that when the transect 3 was longer, so the beach was wider, then the transect 1 was shorter. As from these beach profiles, I also derived 2 beach slopes, so the overall beach slope for the whole length of the profile and the beach face slope between the crest and the step. So for the overall beach slope, we can see that winter was a more reflective profile and spring and summer was dissipative, and we can see that the 3rd transect in the south was the steepest. And as for the beach face slope, we see better this rotation in terms of slope between the different transects, which did not react similarly at during the same surveys, along the year. So winter was also more dissipative as for the beach face slope, and the summer was mixed with the dissipative T1 and the reflective T3. As for the beach width, so length of the profile, I saw that the beach width decreased highly in winter, but not for T1. And we had this jump of increase in beach width over the late winter and early spring. A bit about the visual, and here I want to react again to Carlos' presentation. Maybe you can focus on the two pictures on the right, where you can see on the top, during a rainstorm, the amount of runoff that was found on the beach, from the beach, from the valley bed up to the beach face. And below, you can see the outcome of it a few days after the storm. And so this was a September 2020 storm. So I think we're talking about the same storm. And this year, actually, although I don't have the pictures, we had yet a stronger rainfall, and the whole valley bed with all the plants fell down and it's completely emptied. So that was really impressive as for the beach dynamics. And now to granulometry. We can see that overall the sand was of medium size, and it was well sorted. We found finer sediments in autumn and winter, but for November, and it's more the field observations that suggest that November has such a high granulometry, not because the overall grains were larger, but because they were presence of rather pebbles over an average grain size. As for the beach zones, the finest grains were found in the surf zone, followed by the backshore and the larger grains, and with the largest differences between samples was found in the swash and burn zones. Now this is a bit more detailed with the separation of the different station groups or beach zones. So you have them defined again on top also. So I enlarged this, sorry. And you can see that again, mostly it's the burn and swash zone that were very dynamic. We also had winter more stable as for the sorting. So sorting did not change so much over winter. And finally, for the bathymetry, so here you see the different bathymetry maps that I did. This one is for June, July, August, September, October, November, December, February, and April. So as you can see, the quality of the interpolation depended on the number of points. So this one was a really good survey. And we can clearly see that seaward, the depth increase in summer. Maybe I can do the whole set again. So seaward it increased in summer and then decrease in September and increase again over the winter. While for the longshore bar, we see that it went landward between June and August. Then it disappeared in September and October. And then we see these troughs appearing in December. That's at, I guess, the longshore bar starting back again from a seaward position. As for the other beach I surveyed, so on this second beach, I did only the bathymetric surveys, and we see the same trend of longshore movement with an increased depth seaward between June and December and a decrease in February. And the longshore bar moved landward over the summer, and the same troughs appeared in December. So that would be December, when we see higher depth landward. So overall, the flux was landward in summer and seaward in autumn within the embankment. And the longshore troughs, so close to the beach were created during winter. So as conclusions, these bathymetric data collected with this small USV was precise enough to show seasonal dynamics. Again, it was interesting. It's important to remember that we are talking about a small pocket beach environment. So, for example, satellite-derived bathymetry would completely not have the resolution necessary to observe these dynamics. Then the beach profile was really a very straightforward, although very old method, but it's simple, it's clear, it gives very, very fast this seasonal variation. And somehow, again, obviously, if you have a three-dimensional DEM of the whole area, you get more insights about the geomorphology and dynamics. But this method allows you to see quickly dynamics that maybe in certain contexts cannot be were more expensive, and surveys which demand more resources cannot be led. So as for the sediment fluxes, we saw that on both beaches, they were circular, both cross-shore and along-shore. So as a final word, this tool that I used as a small portable bathymetric measurement tool is very easily deployable, can be used by a single operator, and with this associated camera, it could also be used for different surveys, such as habitat mapping or other repetitive bathymetric measurements. And that will be all. Thank you. I hope I stood within my time, more or less.
Good evening, good afternoon, everyone. It is a great privilege for me to be part of this event today. And I'd like firstly to thank the organizers for gathering us and for organizing it in such a good way. I come from the University of Primorska, that is the literal university in Slovenia. And I'm going to present you a paper with the title, a presentation with the title, Valuing Geodiversity in Different Geomorphic Settings in Slovenia. But first, before I start presenting the results and to discuss them, I would like firstly to define what geodiversity is. When defining geodiversity, one cannot avoid biodiversity, since the whole concept of geodiversity in the scientific community evolved after the concept of biodiversity had already been developed. After the Earth Summit in Rio de Janeiro about 30 years ago, the studies of biodiversity thrived, and they were many of them have been made in the recent decades. We can define biodiversity as the variety of life and its processes. So, namely, we are speaking about the diversity of the living nature, of the living environment. I believe that many of you are familiar with the main evaluation methods that biologists, mainly biologists or biogeographers, use to evaluate and to measure biodiversity of a certain area. They are Simpson's index, Shannon's or Shannon-Weaver's index, then Margolef's index, and so on. Some of them focus mainly on species distribution. Some of them focus on richness, biorichnness. Some of them focus on the even distribution of certain species or genes, or whichever level of biodiversity we choose. When we come to geodiversity, things are not so clear. There is a much smaller number of studies related to geodiversity, which can be defined as the diversity of everything that is not living either on Earth or in any other planet or rock or moon or whichever location. So geodiversity deals with geomorphological, geological, hydrological forms and relief characteristics. So the characteristics of the surface, such as exposure and slope and so on. Both concepts, bio and geodiversity, are intrinsically correlated. They are dependent on each other. And we could say that there cannot be any biodiversity without geodiversity. And if we wanted to compare them or to evaluate nature of a given area in a holistic sense, we should adopt similar strategies or methods for evaluation in both concepts. But when we come to geodiversity, the most common method developed by two Spanish professors makes a great starting point for this, but it does not correlate well with the methods developed by biologists such as Simpson's method or Simpson's index, Shannon's index, and so on. So in this presentation, I'm going to present you in which way I intertwined both methodologies and adapted a part of biodiversity evaluation methods to geodiversity and used them in 3 different environments in Slovenia. You can see that in the second equation under the geodiversity slot. Namely, I used elements of geodiversity that were used already in the first equation, then added the topography characteristics. That's the second part, and then everything was multiplied with Shannon's index or Shannon's evenness index, so that both geo-richness and the geo-evenness of geodiversity elements were equally represented. The procedure was in 5 steps. Firstly, I studied all the available so far literature on geodiversity, as well as some of it on biodiversity evaluation methods. Then I discovered that biodiversity has, I realized that biodiversity has different levels of its evaluation. So we had to find parallels in geodiversity, so in geomorphology, geology, and so on, so that the results could be comparable. The geodiversity index had to be modified, and then it was applied to 3 different study areas, and the results lastly were compared. And in this way, I was able to point to the areas that are most abiotically diverse and that show at the smallest possible area the biggest amount of different either geomorphological, geological, or hydrological forms. Speaking of the hierarchy, with biodiversity, biologists evaluate either biodiversity from the levels of genes, that's the smallest unit, to populations, species, ecosystems, and lastly to the greatest areas covered by living nature with similar characteristics. With geodiversity, there hasn't been any such hierarchy made in the so far literature. So we could speak of geodiversity on micro levels, that these are the microforms. For example, a certain sinkhole, since we were speaking a lot today about sinkholes. Then we have areas within certain microregions, then microregions, then smaller areas with a specific relief type. And then we come to larger areas. We can speak about landscape scale, geodiversity, and lastly to world macro geomorphological areas. In my study, I focused on three areas with a specific relief type, which of course overlaps with other relief types as well. But we could say that they are that they are the areas that can be classified as either post-glacial or fluvial or karst area. So in my study, I evaluated geodiversity of Logarska Dolina, or the Logar Valley Landscape Park, which is a post-glacial area in the north of Slovenia. Then secondly, of the river catchment area of the river Hrastnica. And then lastly, I believe you're all familiar with the classical karst and the Postojna cave system. It is a protected area also above the cave system itself. So I evaluated that region, that area, that in order to get specific data also for the karst environment. So if we look at the three cases in the Logar Valley, there are mainly glacial remains that were, of course, transformed, eroded a bit, and after the last glacier here in this valley retreated. Then the second area is the Hrastnica River catchment area with lots of fluvial forms and their characteristics. And then lastly, the classical karst area above the Postojna cave system with sinkholes and similar forms. To get the common denominator, I used the terrain ruggedness index, which was calculated for the whole of Slovenia. And in this way, the results were comparable among the three areas. So so its values were classified into specific classes, and then those classes were used as specific geodiversity or topographic elements. Now, if we look at the Logar Valley Landscape Park, as I mentioned, it was glacially transformed in the last ice age and before as well. So here we can find various glacial deposits, then boulders, coals, and so on, as well as some hydrological forms. All these forms were mapped and then used for further calculations for calculating geodiversity index. So if we compare the terrain ruggedness only within the park itself, as in the figure A in this picture, the results could be a bit different in comparison to the results of the terrain ruggedness when we derive them from the results of calculating it for the whole of country. So in further calculations, we used this modification of the original formula by Professor Serrano, and so we compared then those results. So we wanted the results to be comparable, whereas in the figure A, if we kept the original formula, the results would be incomparable because the index would be calculated only within the specific areas and not for a wider region. So the highly rugged areas are the ones beneath the coals, and then up to valley floor, down to valley floor, where the ruggedness gets level. There are all the other classes. So if we compare the values of Simpson's index, J is Shannon's evenness index, then index of geodiversity by the original authors, and then the last one with our method, we can see that the most diverse areas are the ones that have either the biggest number of various elements, as well plus the most even distribution of those elements within a certain block of 10,000 square meters. They are mainly on the valley, either on the valley floor or just beneath the cirque systems. Then if we move on to the second study area, that was the fluvial one. Here there are various springs, peaks, two caves, but the most common element here is a creek followed by the river terraces, then alluvial fans, and of course the valley floor. The relief energy in this instance is a bit smaller. Its values are a bit lower. And again, if we compare it within the study area or on the right, in the right picture with the values from the right from the whole of country, we can see that the medium class prevails. So the energy of the relief here is not such so big as it is in the post-glacial landscape. The results show similar picture as with the Logar Valley, the first example that we saw. The highest valley, the highest class of the geodiversity, of the new geodiversity index, is mainly on the valley floor or where the slopes meet the level parts of the study area. In the third case, we mapped springs, caves, peaks, creeks, blind valley, and then numerous collapsed dolines and dolines above the Pustoina cave system, which is a protected area, and it applied the similar methodology. With this case, the surface is mainly level or nearly level, whereas we cannot find here any highly rugged blocks, not even moderately rugged ones. But however, this area is heterogeneous in another way. So the highest geodiversity index in this case, as you can see in the fourth picture, where both even distribution of those elements as well as their numbers, so geo-richness, are multiplied. We can see that the highest geodiversity index is in the blocks with the biggest collapsed dolines combined with sinkholes. And now what I think is the most interesting discovery is that if we compared all three results, if we normalize them once again, we can see that the area with the highest geodiversity index is found only in a fluvial landscape. One could imagine that that could be in a glacial or a post-glacial landscape or in a karst environment, but due to the either in the glacial environment due to the slopes and their inclination, or in the karst environment due to numerous sinkholes. But actually, in these three cases that are typical of Slovenia, it is shown that the most diverse, abiotically diverse region is the fluvial one. So we can conclude by presenting this graph that summarizes the results that have just been discussed, so of the comparison, and that is that the areas with the highest geodiversity index are the ones that employ all these three things, so all that apply to all these three criteria, so that the diversity of the elements is the highest, plus that they are evenly distributed within the region, as well as that there is a high number of variations in the terrain ruggedness, which as well contributes a lot to the geodiversity index, but not with only its high values, but it has to vary. It can also vary from level to nearly level. That makes it more heterogeneous, but not if it is only like 90 degrees inclined. And this is the graph that I would like to end my presentation with. I hope you enjoyed it. Thank you very much for your attention. And now please feel free to ask, comment it, or get in touch with me for a further collaboration. Thank you.
Good afternoon, everybody. I'm Irene from University of Milan in Italy, and I would like to thank the organizer of the event and the Italian Association of Physical Geography and Geomorphology, and all the colleagues that are working with me. And since I will show several study cases, I would like to thank them because I share with them my research. Today, I would like to discuss with you about the role of geomorphology in geoheritage analysis, in particular in the assessment, mapping, dynamics, promotion, and education. So let's start with some terms. Geosites, geomorphosites. Geosites was the first used terms in literature. It was born in 1990s, and it refers to sites of geological interest of very high scientific value. At the beginning of the 21st century, anyway, since the interest toward geosites, but especially toward geomorphological sites of interest, a new term was proposed in literature. It is geomorphosites by Professor Panizza. If we have a short look in the literature list in database like Scopus, Google Scholar, we can find interesting things because geosites is obviously the most recurrent term used, but also geomorphosites as a wide audience in both the database. In 2022, a very interesting book was released by the International Union of Geological Science that contained the 100 most important geosites of the planet Earth. As you can see, they are divided in 8 categories, and the 8th one is the geomorphological and active geological process. It contains the greatest number of sites, 22. And as an example, I take the Grand Canyon in the United States of America. We can see that it was chosen for geomorphology, for fluvial erosion that carved a very interesting and impressive landscape, carving rocks that cover 2 billion years of Earth history. And so there is also a stratigraphic and sedimentological interest due to this stratigraphic succession. Another case that is instead considered for the stratigraphy and sedimentological interest is this stratigraphic section in Spain. Zumaya is very famous. And if we think, we can say that geomorphology is still a very important aspect because coastal dynamics with erosion, gravity-driven processes contribute to expose this stratigraphic section, but probably in geological time, maybe they may contribute also to dismantle it. So geomorphological processes have a relevant role. In the Italian geosite inventory, we can find 2,000 sites. Among them, the 56% is selected for the geomorphology as primary interest, while the 28% as a secondary. If in the IUGS 22% were geomorphological, in Italian is more than a half. That is maybe related to the fact that in Italy we have a geosite database that acquire information also by amateurs and general publics, and attractive landscape are the most considered by the general public. So this may explain this diversity. From the Italian database, we can find another interesting example, like, for example, global stratigraphic section endpoint, like Vrica 1, that is located in southern Italy, assigning the border between Gelasian and Calabrian in the Pleistocene. But if we see at the site, we see again the important role of geomorphology in shaping the stratigraphic section by water runoff, this beautiful badland landscape along the coastal area of Calabria. Another example, we move in the northern part of Italy, in the Italian Alps, where we can see beautiful glacial gorges, where glacial before and fluvial erosion currently are carving the deepest units, the tectonic units of the Alps. So contribute to expose this important section. So in the database, we have in this area 2 geosites, the glacial gorge and tectonic units. But are they 2 really distinct geosites? This is one of the questions I would like to discuss. All the geosites in an area contribute to create the geoheritage. Geoheritage, once again, if we look at the literature, we can see that the geoheritage, geological heritage, geomorphological heritage, we have a lot of terms, and geological heritage is the most successful one, but also geomorphological is important. In 2017, Croatia dedicated a paper to the peculiarity of geomorphological heritage. In particular, they underlined the static dimension, the imbrication of scales, and the dynamic dimension. The first one is strictly related to assessment and promotion, and the second and third related to assessment, promotion, but also mapping issues. According to assessment, the method are customized mainly on geomorphosites. It's a curious this thing, and they relate to scientific value and additional value. Among the scientific value, we have several attributes, and some of them are strictly related to the geological processes too. And we have also transversal value, like geohistorical importance and ecologic support. In a recent review in 2023, some authors underline how many studies related to geological heritage are regard assessment and also geomorphological mapping. Geomorphological mapping opened the way to the second important feature of geomorphological heritage, that is spatial extension and imbrication of scale. This is a short overview on the proposal made by the Italian scientific community to map the geomorphosites on geomorphological map of the Italian Geological Survey, bordering the geomorphosite, the geoheritage sites in general, with a golden line. They could be polygon, polyline, and points. So they may have different geometry according to the spatial scale. We can have point, polyline, polygon, but also simple, composite, and complex geoheritage site according to the genesis they have. This is an example from the Italian Alps. Once again, this is a beautiful rock pillar. It is in the Sesia Val Grande UNESCO Global Geopark. It is a point feature. It is a simple because it's related to one most important genetic process. And it may have regional, national, or international. But we have, in a geomorphological view, also complex situations, like, for example, this. We have a connection between two proglacial plains. We have several landforms of different origin in a very, in a relative small area. This is another site located along the coast where we are working on. And it is very important, the role in geomorphology in this case, because we can move from the single point site that is a cave, where important, very relevant archaeological remnants are included, to wider the view over the entire coastal area to understand sea level change and how it influenced the human settlement in the area. Other complex situations are found in the Alps, where this slope is characterized by a deep-seated gravitational slope deformation, but inside this single element we can find several subsites of geomorphological and geological interest strictly related to the deep-seated gravitational slope deformation. So how can we manage this complex site? How can we promote a slope scale site with several nested sites? Another an option could be the viewpoint geosite. That is another way to appreciate the geomorphological landscape from an external point of view. Once again, imbrication of scale. The third characteristic is related to dynamic dimension. We have the geomorphological processes that act on geoheritage sites. They can be the genetic one, like in case of active sites. These genetic processes are not active anymore, or they are shaping other type of landforms that have a different genetic origin. But what this implies? This implies that integrity and representativeness of a geoheritage site could change, and we can lose a scientific value of site. Some examples are related to cultural value too, because we have this beautiful village in the central Italy that are affected by erosion, by gravity and water on clays, for example, isolating this beautiful village. Other examples are the change of ecological support role of landforms. We are in a glacial environment where vegetation is strongly affected by glacial advanced on retreat and glacial hydrological variation. We are in karst environment here and also in water runoff on the right with shallow landslide that involve several trees in the geoheritage site area. Once again, the ecological support role is variated by the deep-seated gravitational slope deformation on the left or by snow avalanches affected site of geomorphological and geological interest. In the last year, several attempts are made to quantify the sensitivity of site to this degradation, and we can have a fragility, vulnerability analysis to detect which are the intrinsic and extrinsic natural and anthropic processes degrading the geoheritage site. And Selmi, for example, proposed very recently an index of degradation to quantify this change that could be quantified by monitoring methods that are multidisciplinary, like strictly photogrammetric or morphometric measurements using vegetation like the endogeomorphology to assess this rate of change. But when we speak about dynamics, we speak also about hazard. And when we are dealing with promotion, we have to deal with hazards that can affect, for example, thematic trail like this in the Solda Valley in the central Italian Alps. And this hazard may become, in a certain way, also a resource, because from site of geomorphological interest, like the Vajont landslide, one of the IUGS site that was responsible for 2,000 victims in Italy in the 1963. And this hazard may mine in cultural value, like in this case where we have in the central Italy, very important village located above these rock outcrops. But we can also use dynamics to communicate this evolution of the landscape, to map this, to also increase awareness in people about to use a dynamic landscape that is also a resource. Last but not least, and my colleague before speak a lot about geodiversity, we have also geodiversity and geomorphodiversity. This is important, but geomorphodiversity is not still a very common used term, and is based on the fact that we have a natural range of geomorphological different landforms and processes, and we can speak with this proper term that is not so common now. As geodiversity, also geomorphodiversity offer abiotic ecosystem services like regulating, provisioning, supporting, and culture, and this it were to have a specific talk about this. I only give you this example of proglacial areas once again, where we have a very complex system, imbrication of scale, aesthetic dimension, and dynamics that can change not only local supporting provisional cultural and regulating services, but also down valley, influencing very far from the geoheritage site area, this type of abiotic ecosystem service. So, concluding, as you can see, assessment, mapping, dynamics, promotion, and education are strictly connected, especially looking at the geomorphologic dimension of the geoheritage site. So I tried to show you how geomorphology contributes deeply to heritage analysis through the aesthetic value, obviously, that attract the general public, the imbrication of scale that asks for specific management strategies for each site, and dynamics that affect different type of heritage site, both natural and anthropic, and also influence promotion because it may generate potential hazards. So to conclude, geoheritage is in reality a unique box where single site can be identified with their own features. We can have a main interest, but we have to remember that the system works as a whole and should be treated as a single, even if complex element. Thank you very much.